Hi, good evening. We're going to get started. So just a quick reminder that tomorrow we're going to have a quiz 4. That's going to cover 7.4, which is partial fractions. That's integration. There is partial fractions. And also cover 7.8 improper integrals. And also 11.1, which we're going to talk about today. Yeah, Sam, if you have any questions, let me know. We can go with 11.1, which is going to be on sequence. So let's begin with going over any homework questions that you might have. Negative. Excellent. I was about to go over this question. I'm glad you brought it up. Good. So yeah, so Sam has a question. I think Aiden also had it a few days ago. Yesterday he asked me. So great. So we're just going to take this example. We're integrating from negative infinity to 0 of x over. I'm not going to use x to the fourth power plus 4. I'm going to see x to the fourth power plus 9 dx, right? Just so that you gain the practice, about solving this problem later when you go back to the question in the homework. Is that okay, Sam?
Yeah.
Okay, great. So the first thing I'm going to do by just looking at it, in the denominator, I'm going to rewrite the 9 as a 3 squared, and I'm going to write the x to the fourth power as x squared, because when I first see this problem, what I see is that I have an x in the numerator, then I have x to the fourth in the denominator. So I'm thinking, if instead of x to the fourth, if I had x squared there, then the numerator is almost the derivative of x squared, right? So that's what I was thinking. I was like, oh, maybe I should have an x squared somewhere. So the first thing I'm going to do, I'm going to rewrite this integral as x over x squared. So that's x to the fourth plus 9 dx. And now I can set u to be x squared, then du will be 2x dx. That would be perfect because I have x in the numerator and a dx on the side. So that's sort of the motivation there. Before I do that, I'm going to rewrite this integral using limit notation because it's going from a negative infinity to a constant 0. So that's an improper integral here. It's okay to use a definition. Let's try it. We don't know if the limit exists or not, but let's try it. We're going to use limit t going to negative infinity, integral from t to 0, x over x squared plus 9. I said I'm going to put it as 3 squared dx. You don't have to do it now, but I want to put it in that way so you can see the pattern in a minute. So the next step is I'm going to let u to be x squared using substitution. Du equals 2x dx. Here you can solve for dx, which is 1 over 2x du. Substitute into the integral. So from here, I'm going to begin in the next line on the left. So that becomes the limit. I hope it's okay if I don't write the limit for t. So that's just a limit. Integrating. Remember that there's two values. One is t, the other one is 0, but I'm not writing them now because they don't really get involved yet. I'm just being a little bit lazy here. X over u squared, that's x squared, that's u squared, plus 3 squared, that's 9. and the dx becomes 1 over 2x du. Immediately, I can cancel out the x in the denominator and the x in the numerator. And I have a 1/2 as a constant. So I'm going to bring the 1/2 in front of the integral, but then you know the 1/2 doesn't get involved when we take a limit. So we can bring 1/2 all the way outside. Just get it out of the way. So that's a 1/2 limit. And this is a definite integral. We have two terms that we're going to use later. Then I have x cancel, the 1/2 is gone. So I just have 1 over u squared plus 3 squared du. This is from t to 0, then have t go into negative infinity. The next step is I'm going to focus on the integral, right? If you remember in those questions with those, we have to find the definite integral, find the antiderivative, plug in t, plug in 0, and then take the limit, right? So let's focus on finding the antiderivative of 1 over u squared plus 3 squared. You can look at the special formulas because that really is integrating 1 over x squared plus a squared dx. So that's a formula you can follow. Or you can just look at it. Since we're working with x squared plus a squared, why don't we try to use the triangle, the trig substitution? So I'm going to say, since I have u squared and a 3 squared, so I'm going to call this u, call this 3, call this theta. And from the right triangle, I have tangent theta is equal to u over 3. So u equals 3 tangent theta in my example. That's a good point. Sam, I'm glad you brought it up. So the u substitution that works really well when we had like a square root of x squared plus a squared, right? It also works well when you just have x squared plus a squared. It works well in both cases. So yeah, absolutely, you can use trig substitution here. And carry out the steps. So the du we need because we have the du in the integral. So that's a 3 secant squared theta. And then u squared plus 3 squared, I can find it on the side before I plug into the integral. So u squared plus 3 squared, that's going to be 3 tangent theta squared. So that's a 9 tangent squared theta plus 3 squared, which is 9. Again, you can keep it as 3 squared. But for now, just 9 is fine. So that's a 9 tangent squared theta plus 1. And if you remember the identity, that's going to be 9 secant squared theta. Aiden, this part is where I got a mistake last when I was helping you. I think I wrote a 3. Whatever the example I had, I didn't keep it as a 9 equivalently. So that's u squared plus 3 squared. So now I'm going to put into the integral. I have 1/2 limit integrating from t to 0. And obviously limit has t going to negative infinity. 1 is 1, u squared plus 3 squared, that's 9 secant squared theta. And the du is 3 secant squared theta d theta. Oh, I forgot a d theta. Sorry about that. It's important. And from here, I can cancel out the secant squared theta in the denominator and on the side. Under the 3 and a 9, I can calculate that that's 1/3. I can bring it outside. So the 3 and the 9, that give me a 1. This give me a 3. So that just give me a 1/3. I'm going to bring it outside, combine it with 1/2. So you got 1/6. Limit t going to negative infinity, integrating t to 0 of d theta, just 1 d theta, right? Just d theta there. that becomes a 1/6 limit t going to negative infinity, theta evaluated from t to 0. But be careful here. What is what's the 0 for? In the given question here, 0 is the x value, right? Negative infinity is also x value. So you should be very careful. So even though we have theta going, we need to evaluate that from t to 0, but those are really x values. They're not theta values, so we cannot plug in directly. So now I'm going to have to go back to try to rewrite theta in terms of x, and then I can plug in. Obviously, you can find the new boundary for theta first if you like, but I don't like to do that. So from here, how do we write theta in terms of x? Well, I know that tangent theta, so note, earlier we had tangent theta equals u over 3. Then I can find theta in terms of u first. Theta is equal to inverse tangent of u over 3. You probably wonder, oh, that still doesn't help us. Well, that's like one step closer to getting x, right? Because we know u in terms of x. So that's one relationship we're going to use when we go backwards. The second one we use is u equals x squared. So this equals inverse tangent, u is x squared, so x squared over 3. So now we get theta in terms of x, I can put back into the limit. So that's equal to 1/6 limit t going to negative infinity of inverse tangent of x squared over 3. Evaluated from t to 0, those are x values, perfect. Now let's find the value, let's plug in 0 and t. So we have 1/6 limit t going to negative infinity, and then I'm going to plug in 0 first, so I get inverse tangent of 0. Now I'm going to plug in t, so minus inverse tangent of t squared over 3. We have to evaluate each one of them. If you recall that inverse tangent of 0, so look at let's consider the graph of tangent. It looks like this. This is a tangent theta or x, I guess in the matter. So here the inverse tangent is that you know the y value, you're looking for the x value. You know the y value is 0, we're looking for the x value. So if the y value is 0, the x value has to be 0, right? In this case, the x is not x, it's really theta or some variable for the matter. So this is the angle. This is a tangent theta value. So this part becomes a 0. The other part, I don't know, I have a t, so let's do that next step. So we got 1/6 limit t going to negative infinity of negative inverse tan. So I'm going to bring the negative outside. Inverse tangent of t squared over 3. So if I put negative infinity for t, what do I get? I get negative 1/6. This is not appropriate, but I'm just going to write like this. Put negative infinity in there, so I get inverse tangent of negative infinity squared over 3. That's just infinity over 3, which is also infinity. The parentheses part is just infinity. So I end up with negative 1/6 inverse tangent of infinity. So you probably wonder, how do I find out this part? Inverse tangent of infinity. This one says the y value is infinity. So the y value is infinity. What is the angle? Well, if the y value is infinity, it's somewhere here. What is the angle? The angle is corresponding to this angle, right? What is that number? That's pi over 2. So as y approach to infinity, the angle will approach to pi over 2. So this is the inverse tangent of infinity is pi over 2. Use a graph helps a lot, many times. So that should be your answer. Any questions on that?
Could you scroll down a little bit? I went to the bottom.
Oh yeah, I didn't write much after that line. So this problem is tricky because at the beginning you have to use a u-substitute. You obviously write the x to the 4th power as x squared. Use the u-substitution there, and turn it into an integral of u. And then you have to use trig substitution if you don't know how to integrate that directly. If you use trig substitution, and after you find the definite integral, you have to go back and write in terms of x, then take the limit at the end. So it requires multiple steps, but if you kind of break it down into different sections of solving this problem, it's you know everything, right? I'm pretty sure that we cover everything in this process. All right, so that's that question. Any other comments or questions about this particular problem or about any other homework questions? Go ahead, Chris. All right, negative infinity to infinity. All right, so the next question is, integrating from negative infinity to positive infinity of x e to the 3x dx. To the negative x squared. Negative. Okay. It doesn't matter if it's a negative 3x squared or negative x squared, right? It's a constant that wouldn't make a difference. But for now, let's just take this example. So this one, let's just look at it. Is there any discontinuity in this case? No, right? That's good because that's just like all the problem we have. But it's going from negative infinity to positive infinity. So the lower bound is infinity, the upper bound is also infinity. So we don't like this. Let's take this infinity, let's just pick a value in the middle to divide it into 2 intervals. So I'm going to pick 0. So I'm going to write this as integral from negative infinity to 0 of 17x e to the negative x squared dx plus integral from 0 to infinity of 17x e to the negative x squared dx. Now, it's okay to write like this if both of them are convergent. That's the definition. And we don't know if they're convergent or not, but let's just start writing like this and let's see if we run into problems. If we figure out one of them is not convergent, then we can just stop, right? Let's just leave it like this, and then we're going to work on. I'm going to work on one of them, and then you can finish the other one on your own. So let's say we take this one, and then we're going to use the other definition because we still have a negative infinity here. So we're going to use the limit definition. So just the first part, the first integral here, limit negative infinity to 0, 17x e to the negative x squared dx. I'm going to write as limit t going to negative infinity of integral t to 0, 17x e to the negative x squared dx. And then this integral part, by just looking at it, the integrand, the function in the middle, I see a x, and I also see e to the negative x squared, but it looks like the x is the derivative of the x squared or negative x squared, doesn't matter. It looks like that's a derivative. So that means I can try to use the u-substitution. Let's try that. So I'm going to let u equals negative x squared du equals negative 2x dx, and then I can solve for dx, which is 1 over negative 2x du. Let's substitute into the integral, see if it helps. So the integral, the limit stays integral 17x times e to the u, and then I have dx, which is a 1 over negative 2x du, which becomes limit integral. The x in the denominator and the x on the side, they cancel, right? And the negative 1/2, I'm going to bring it all the way outside. So I get negative 1/2. And the 17, obviously, I'm going to put it outside too. Forgot to do that. So negative 17 over 2. Limit. And then I just have 17 is gone, x is gone, negative 1 over 2x is gone. So I get e to the u du. Absolutely. Yep. Good point. Yes. So this is what I always keep in mind when I work on problem like this. Every time I have a constant, I can always bring constant in front of the integral, in front of the limit. Just sort of like put it outside, put it away, have less to work with. So remember that this integral we have from t to 0, and then the limit is going from t to negative infinity, right? So that's a negative 17 over 2 limit. And we're integrating e to the u du, that's a e to the u, but evaluate it from t to 0. But keep in mind that those are x values, those are not u values, so we cannot plug in directly, just like the previous example. Now we can put in the u there. So that's negative 17 over 2 limit e to the negative x squared, evaluate from t to 0. That's negative 17 over 2 limit. Now I'm going to plug in the 0, plug in t, so that's a e to the negative 0 squared. That's a e to the negative 0, just e to the 0. You can figure out what that is. A minus e to the negative t squared. And then t going to negative infinity. And just keep carrying along the constant. The first term, the e to the 0, that's just 1, if you recall. And then the second one, I'm going to evaluate as t goes to negative infinity. But the first thing I'm going to do is I'm going to bring the negative outside, this negative right here. Put it with a negative 17 over 2. So that's a positive 17 over 2. Limit t going to negative infinity of just e to the negative t squared. And I really don't like, I don't like a negative exponent when I try to evaluate the limit. It doesn't help. So I'm going to rewrite this as a 1 over e to the t squared. I hope you're okay with that notation. And then this one, we can try to evaluate the limit. So 17 over 2 state. Oh, I forgot a 1. Sorry, 1. Oh my goodness, I messed up, didn't I? Sorry. Let me take a couple of steps back. So I cannot take out the negative outside. Let me take that back because I have a 1 there, not a 0. So we just have to evaluate the limit directly then. So that's a negative 17 over 2. I'm going to take negative infinity, replace t. So that's a 1 minus e to the negative of negative infinity squared. Sorry about the confusion earlier. That's a negative 17 over 2. 1 is just 1 minus e to the negative infinity squared. Negative infinity squared become positive infinity, but you still have a negative e to the negative infinity. I don't like the negative infinity in the exponent, so I'm going to rewrite the e term. So that's a negative 17 over 2. 1 minus 1 over e to the infinity. And hopefully you can see it from here. If you have e to the infinity in the denominator, that is just infinity in the denominator, right? And a 1 over infinity, so 1 over infinity, that's approaching 0. As the denominator gets really bigger, that's really small, right? So this basically the 1 over e to the infinity term goes to 0. You just have 1 left. So at the end, it's just negative 17 over 2 of 1 minus 0. It's just negative 17 over 2. So that's this one on the left. We were able to find a limit, right? So that means the first term, the first integral that we had earlier, this term, this integral is convergent. That's good. That's important for us to try to find the integral that we begin with. Right, so that's good. And then the next step is you take the other integral. You follow the same steps, 0 to infinity, 17x e to the negative x squared dx. And you're going to try to do the same thing. If you end up with a finite value when you take the limit at the end, that's a good sign. That means the second integral, this one is also convergent. Then you can take the two values, put them together to find the value for the integral that's given from negative infinity to positive infinity. This is a good question. I just want to point out that we pick a value x equals 0 in the middle. You don't have to pick 0. You can pick a 1. That's a sort of the breaking point for the interval from negative infinity to infinity. You can pick 2 or you can pick any number in the middle. It doesn't make a difference. It shouldn't make a difference, I think. But 0 is the easiest. All right, so I hope it's okay if I don't continue this. So try it on your own to do the second part, and if you still have questions, feel free to let me know. Any other questions?
So is the final answer for this one negative 17 over 2, or what would you do next?
No, that's not the final answer. That's only the answer for the, remember we take the integral we divide it into two integrals adding, right? So the negative 17 over 2, it's only the integral for the first, it's the value for the first integral.
Oh, okay.
Yeah, it's this integral, we were able to find a limit for it's negative 17 over 2. Then you have to still figure out what that second one is. It maybe it's not convergent, right? We don't know. But if you follow the steps I did, you should be okay to figure out the second part. Right. So yeah, Aiden has a good point. I don't know if you guys see that. Right. So the integral, if you look at the function inside, that's exactly the same. It's the lower and upper bound is different. That's what Aiden pointed out. So everything's the same basically until you get to well, I guess somewhere here. I mean, even like probably here, because it just the values you plug in will be slightly different. And then when you take the limit, it will be different. So you wouldn't have to do a lot of like different work from the beginning. Good point. That would be a good practice. All right. So that's this question. Any other questions? All right, I'm not hearing any comments. I do have to move on to the next section because it will be on the quiz, but I don't think it's very difficult because most of it, I think you have to sing it before in a high school calculus, probably not calculus, like a maybe pre-calculus class. So if you don't have any comments, I'm going to move on. So now we finished 7.8, we move on to chapter 11. So for the rest of the summer semester, we're going to just focus on chapter 11, which is on sequence and the series. So let's just do a quick review. I don't know if you remember. So 11.1 is on sequence. So what is a sequence? So definition, a sequence is just a list of numbers. It could be a finite sequence or infinite. So the list could be finite or infinite. For now, we're only gonna focus on infinite sequence. For example, if we have a list of numbers like 1/2, 1/3, 1/1, just one, right? 1, 1/2, 1/3, 1/4, and so on. This list of numbers, that's a sequence. You could also have 1, 1, 2, 3, 5, 8. I don't know if you've seen this before. This is called the Fibonacci sequence. Those values, they sometimes I don't know very well about Fibonacci sequence, but I think those numbers they're very useful in different parts of mathematics. Just like the Pascal triangle. No, not the Pascal triangle. So that's a sequence, and then the next thing is the general form. We usually take a sequence we write as A1, means the first term, first element. A2 means the second element. A3 means the third element, and so on. We may end up at n, so an is the nth element. So A1, A2, A3, or an, those could be values, could be some algebraic expression. Depends. but we use, so given the sequence, we can, if it has a pattern, right, then we can write a formula, a formula for that, for the elements in that sequence. So formulas. For example, the example I gave earlier, I have 1/2, 1/3, 1/4, and this is the first element, this is the second, this is the third, this is the fourth, and then we can write a formula that represents the element in that sequence. So this is probably not new to you, so I'm just going to write it down. So the formula for that example would be just 1/n for n. This is like a curly brackets for n going from 1 to infinity. In that sequence, I didn't put an n, it continues. So the first element, if I take 1 put in there for n, so I got 1/1, 1. So that's the first element. If I take 2 put in there for n, so I got 1/2. If I take 3 put in there, I got 1/3, and so on. So this is the formula for that sequence. 1, 1/2, 1/3, and so on. How about the Fibonacci sequence? Can we also find a formula to represent the element in there? Not in the sense that we just wrote. The Fibonacci sequence, we have 1, 1, 2, 3. It's difficult to find the formula that applies to all terms, right? Like just change the n to get all the elements. It's difficult, but for the Fibonacci sequence, what we can see is that we can see the first element, the A1 is always 1. You treat it kind of like a proof and then have a given section. We are the stuff that we're talking about now, that's sort of like fruit, like a material that will show up in a class that yes, exactly. That's what we call the recursive pattern, recursive rule. That's right. So Aiden, so good point. I was going to mention that at the end. So we're going to have to use a different way to describe the elements by using previous elements to describe the upcoming elements. So A1, I'm going to call it 1. A2, it's also 1, but A3, what depends on A1 and A2, right? A3 is 1 plus 1. So that's a A1 plus A2. And the A4 is equal to the fourth element is 3. So that's a 1 plus 2. That's the previous 2 added. So I can write as A2 plus A3. And A5, which is 5, which is 2 plus 3. So that's a A3 plus A4. Hopefully you can see that except for the first 2 elements, starting the third one, they all have this pattern of adding previous 2, right? Like Aiden said. So what we're going to do is we're just going to write a new rule saying, given A1 equals A2 equals 1, AN is equal to AN minus 1, the element before n, plus AN minus 2, the 2 elements before the nth term. So this is the rule that will describe all elements in that sequence, in the Fibonacci sequence, with a condition that n greater or equal to 3, right? Because if n equals 1, that wouldn't work. If n equals 2, that also doesn't work. This kind of rule is what we call a recursive. I don't think I can spell it right. You know what? I'm going to just leave it there. You can look it up. So that's a different rule as a formula that we had for the sequence 1, 1/2, 1/3, right? So that's that one. We can just write a formula that will apply, just change the n to get all the elements. For the Fibonacci sequence, you can only define a upcoming element by using previous, the element before it, or 2 elements before that, or 3 elements before that. But again, that's also a sequence, right? Just different rules to describe that. So that's formulas. And another example I have is that if I have a sequence 1/2, -1/4, +1/8, -1/16, and it continues. Can we figure out a formula for this? Doesn't matter whether it's a recurrence formula or the just a formula, change n. But if we look at this, the difference are 2 differences, right? One is it going from positive to negative to positive to negative, so the sign alternates. The second part is that the denominator going from 2 to 4 to 8 to 16. There's a pattern there. So what is a pattern? Well, we got 2, which is 2 to the first power. 4 is 2 squared. 8 is 2 cubed. 16 is 2 fourths. So for the times negative, probably not negative 0.5, right? Except for the first one, right? So, okay, good. Yep. It is right. So multiply by -1/2, except for the first one, right? So that's helpful. You can actually write a formula by looking at the ratio. Good. So it is multiplied by -1/2 each time. Right. So in fact, this is what we call a geometric sequence, because the ratio between adjacent terms are the same. So you can find there's a formula to write a geometric sequence, which I'm not going to use here because I want to show you that even if you don't know that formula, you can still figure out the pattern. The pattern for me, from what I'm seeing, is that looks like the denominator is always going to be 2 to the power of n, for n going from 1 to 2 to 3, right? 2 to the first, 2 to the second, 2 to the third. The only thing that changes is the exponent of the 2 in the denominator that changes. Well, what about the numerator? The numerator looks like it's always 1, but then because I have the sign alternates, so every time you have a sign alternates, it's always going to be a -1 raised to a power. Is it to the n or to the n minus 1 or n plus 1? Then you have to decide. If it's just to the n, that's not right, because if n is 1, the numerator should be positive, but if n is 1, I have a -1. That's not okay. So it should be n plus 1 for the numerator, or for the term that you multiply with, right? So that's the same, that's sort of the trick that I learned. You don't have to look for specific patterns. Obviously, it's easy. Like, I mean, the formula for geometric sequence, it will be easy, but a lot of times you can probably just do your best, try to figure it out by looking at how different parts of the given terms change. So for Daniel and Sam, that's, you know, what you said is correct. That's a good observation. but I'm not using the fact that it has a constant ratio to pick up the formula. Does n equals 1 here? So for this, yes, n begin from 1. So that's going to be 2 in the denominator and a 1 in the numerator to infinity. For us, we always keep it n going from 1 to infinity. So n equals 1 means the first element. So n equals 1, it means it corresponds to the first element. Of the sequence. And if we given a formula for sequence, we can go back, write out expand the sequence, the first few terms of the sequence. For example, n plus 1 over n squared for n going from 1 to infinity. This part usually is the easiest because you just take n, you put in there each time, right? So the first element would be taking 1 put in there. So I got 1 plus 1 over 1 squared. The second element will be taking 2 put in there. So 2 plus 1 over 2 squared. Take 3 put in there, 3 plus 1 over 3 squared. And then simplify a bit if you can. So that's a 2 over 1, just 2. That's a 3 over 4. That's a 4 over 9. And it continues. Right, so that's an easier one. Any questions on those parts? Because for the next probably 15 minutes, I'm going to write down a lot of definitions, properties, theorems, and then we look at some exercise. It's also in the book, but I do want to write them down in case some of you probably prefer to take notes. So when does this get complicated? It depends how comfortable you are. I think you might find what I wrote right here. Brian's right. It might get complicated soon, right? Anyway, I'm going to start writing on the definitions because it depends whether you have taken any classes on analysis, if like a real analysis or complex analysis or functional analysis. The reason I know them because I have taken them before. So it could get abstract for some of you because obviously we're not really getting to the proof part, but there's a lot of theorems, you know, I have to use it. All right, I'm going to start writing. So for limits, so remember we talked about limits before, right? When we have a function, we can talk about limits, but for sequence, we can also talk about limits. So definition of limits, of a sequence. For a sequence, if an means the nth element, if you remember that earlier, so an is the nth element, right? So if an approaches L, some constant L, as n goes to infinity, then L is the limit of sequence an. this curly bracket with an means a sequence going from n equals 1 to infinity. So if as n increases, you look at the element in that sequence, as n going from 1 to 2 to 3, all the way going towards infinity. If the value for in the sequence approaching some number L, then the L is a limit. Another notation is limit n goes to infinity of an equals L. So that's as n goes to infinity, the limit of the sequence an equals L. So that's the intuitive definition of limit of sequence. You can try to think about an as like sort of the formula for the elements in the sequence. It's kind of like an f of x, right? So try to relate this to, when you see this, try to think about limit x goes to infinity, f of x equals L, or something like that. So the x is like the n is the input, so n is the input here. An is like the f of x, so an is a formula for the nth element, just like f of x is a y value for a certain x value. But this is a discrete because the n can only go from 1 to 2 to 3 to 4, right? It's not continuous. This one is continuous. All right, a precise definition of limit. A sequence. Here's where it gets confusing if you're not familiar with the language. So I'm going to use a few abbreviations. So a sequence an, again, it's going from n equals 1 to infinity, but I'm not writing it as limit L, and we write as limit n goes to infinity, an equals L, if for every epsilon is some small number greater than 0, for some small number that's greater than 0, there is a corresponding number n integer n, capital N, such that, this means such that, I don't know if you've seen it before, so let me note, such that for all n, so this means for all, for every, for all means the same. So this is a basically upside down A. It means for all. So for all lowercase n greater than capital N, an minus L absolute value less than epsilon. So that's a formal definition. It's really confusing if you haven't seen it before. It probably take, you have to read it a few times to try to understand it. But what this definition says, let's just see we have I'm going to try to draw a diagram. So let's see we have some sequence, so n equals 1, n equals 2, n equals 3. The values in the sequence are like this. So each of this point I'm plotting is a value in the sequence, right? So try to think in that way. So those are values in the sequence. So what this definition says, if for every epsilon greater than 0. The epsilon could change as long as it's greater than 0, but it's very small. So this is a small epsilon, very small. That's a corresponding n, integer n. So if you pick an epsilon, there's some integer n such that for all lowercase n greater than that integer, so n is here or beyond any n greater than capital N, such that for all n greater than capital N, the absolute value of an minus L is less than epsilon. So what that says is that, so here you have a L, so this is the L is a Y value, so this is L, such that if you pick an epsilon, this part and this part, this is L plus epsilon, this is L minus epsilon, so that all the A sub n, the value in the sequence, will fall between those two boundaries, so the L minus epsilon and the L plus epsilon boundary. So let me label this. This means each of this point here, it just means an. So that's what that definition says. If you pick a different epsilon, you're going to be able to find a different capital N, such that, you know, all the elements after that capital N will be between L plus epsilon and L minus epsilon for the new epsilon you pick. So that's the precise definition. You know, obviously we're not going to do the proof in this class, but you should read it and try to at least understand the diagram. I probably didn't do a good job drawing it. Yeah, try to understand it as much as you can. I'm not going to put a quiz, put a you know, something like this on the quiz, obviously, but it's just a definition. And if you're planning on taking a lot of math class in the future, very likely you're gonna, like, let's say math or I don't know about engineering, like some kind of mathematics is your major, you're gonna have to get really comfortable with this kind of language. But don't worry, you know, the more you learn about this topic, the better you're gonna be at this. You're gonna do well in the future. It takes practice, right? So that's the definition of limit of a sequence. Now here's a let me see, which one should I write? I'm going to write down a few properties. I think that's easier to understand. So properties of limits of sequences. So here, so in the following, if you see limit an, just think about it's the limit of the sequence an, not just the individual element, right? It's the limit of the sequence. So if we take the limit of n goes to infinity, I should give myself some space, of the sequence an plus the sequence of bn, if we want to find that limit, we can just find the limit of each of them separately and add them together. This is nothing new, just like a limit of f plus f of x plus g of x. You can find the limit of each function separately, right? This is called the sum law. It's the same property we have used with continuous functions. Now, what if we have a subtraction? If we have subtraction, it's the same. So this is the sum and the difference law. I'm just going to put it together. The next one, if we take the limit of a constant c times elements of the sequence an, and as n goes to infinity, the constant, I can bring it outside as always. It doesn't really change much when I take the limit. So that's going to be c times the limit of the sequence an as n goes to infinity. This is called the constant law. And if we take the limit of a product of the elements of sequence an and then the element of sequence bn, if we multiply them and take the limit, it's just the same thing as if we take the limit of each of them separately and then multiply the limits together. This is the product law. And then obviously there's the quotient law. It's the same format. So if you have a limit, n goes to infinity of an over bn, that's going to be equal to the quotient of limits. Okay, and then there's the power law. If you take the limit of an raised to the power p as n goes to infinity, so you have a sequence an and each element is being raised to the power p, the constant power p, and then you want to know the limit. That's the same. You're going to get the same thing if you just take the limit of the sequence first and then find the limit, raise it to p, to the power p. Okay. Now the next part is called so those are the properties. The next part is the theorem. I'm going to write down this one, then I'm going to write down another one before we jump. Oh, that's 3 theorems. Let me write down all of them, I think. So the first one is that, so if limit f of x is equal to L as x goes to infinity. So if a continuous function with x goes to infinity, the function approach L, and f of n equals an. So if x equals n, we get the y value is the same thing as the value in the sequence, where n is an integer, then limit n goes to infinity, an is equal to limit x goes to infinity, f of x is equal to L. This theorem says if the limit of a continuous function that exists and it's approaching L, and also the function depend on x will give you the same value as a sequence that depends on n, then the limit of the sequence, this one, is equal to the limit of the function, is whatever the function approach to L. So a diagram might help. For example, if I have a function that looks like this, it's approaching L. So this is a value, oops. So this is the value L. So the function approach that, the y value L. Right, so the limit of the function exists and the limit is L as x increases. And if for every x there being integer, say x equals 1, f1 is this value, and this is also a1, and x equals 2, this is the f2, which is also a2. This is the x equals 3, this is also a3, f of 3, and then so on. So whenever x is an integer, the y value is the same thing as the value in the sequence, that a1, a2, and so on, right? Then that sequence will have the same limit as the function, both limits equal to L. That's what this theorem says. This is useful. I'm going to show you an example later. When we want to find the limit of some, sequence, we don't see it directly. We can always rewrite the sequence, the an, using f of x, and use that continuous function to find the limit there. So note, we can use limit x going to infinity f of x to find the limit of sequence, not n goes to infinity an. So that's the benefit of this theorem. I'm going to show you one example, or one or two examples on this. Let me finish writing the second theorem, which it's called the squeeze. It's also the sandwich theorem. It's a very famous theorem. It's called the squeeze. I don't know if I spell squeeze correctly, but anyway, the squeeze theorem. It says if we have a sequence an and the sequence bn and also sequence cn, if the elements an less than or equal to bn less than or equal to cn for all, so for all, I'm going to use this notation, upside down a, so this means for all. So for all n greater or equal to capital N, and if we know that the limit of an we know as n goes to infinity is equal to the limit of cn as n goes to infinity. So the sequence, the an sequence has the same limit as the cn sequence, both equal to L. Then the limit of the sequence bn as n goes to infinity is also equal to L. I'm going to use a very simple diagram, hopefully, to show this. Let's just see, we have, this is the an sequence. Let's just see the an, they approach some number. Let me use this color to draw the limit. So let's see, this is the limit. So the an sequence approaching that limit. And the C, oh, I did draw it wrong. Sorry, I draw it, let's call it Cn. Cn approaches that limit L. And then the an is less than Cn for every n there. But it's also approaching the same limit. So it's approaching that L. And the bn, which is a sequence that for any n is always caught, it's always between the an and the cn. So bn is in the middle. So let's see, bn could be like this. Right, doesn't matter, doesn't have to, be straight line, same constant value, or doesn't have to line on a straight line, but let's just see, this is the sequence of bn. But it's always between cn and an. So if you have an is approaching, it's the lowest value, it's approaching L, and the Cn is the highest value, it's also approaching L, then the Bn caught between them has to approach L in the middle, right? It couldn't pass beyond it. So that's called the squeeze theorem. And then the last one, theorem 3, is the absolute. It's not an absolute. I don't know what you call this, but anyway, just a theorem. So if we know that limit as n goes to infinity of absolute value an equals 0, then the limit as n goes to infinity of just an, if you drop the absolute value sign, that's also going to be 0. Correct. So that is also, that's a lowercase n greater or equal to capital N. The reason we keep this capital N here, it doesn't really matter whether it's greater than or equal to, whether it's a greater than n or greater or equal to n. That equal sign really doesn't make a huge difference. Barely make any difference in all the cases. Because remember that capital N is some arbitrary number, right? Lowercase n is just greater than that arbitrary number. So you can always redefine the n to make it work, like just to be the next n or the previous n. So this equal sign doesn't make a difference. Thank you. So this is the theorem. I'm going to quickly show you the proof that's from the book. So proof, very brief. I think it's understandable. Proof, we know that absolute value of an, remember an is elements from a sequence. So for any given lowercase n, that's a number, right, or value. So this an with absolute value is always going to be greater than or equal to the negative of this, or going to be less than or equal to the positive of an if an is positive. Oh no, I wrote it wrong. Sorry. What I'm writing. Clearly, I shouldn't just copy from the book. So an is always going to be greater or equal to negative absolute value of an, less than or equal to absolute value of an. Okay, that makes more sense. For example, if we have an is 5, we know that 5 is always going to be less than or equal to absolute value of 5 because that's positive, greater than or equal to negative absolute value of 5, which is negative 5. Or if we have a negative 2, we know that's always going to be less than or equal to absolute value of negative 2, which is positive 2, greater or equal to negative of absolute value of negative 2. That relationship is always true, right? So we know this relationship here. So the an without absolute value sign is caught between those two. Now, what is the limit on the left? So what is the limit of negative absolute value sign of absolute value of an as n goes to infinity? Well, the negative is a constant. Remember the property, we can bring constant outside. So that's just going to be a negative limit. N goes to infinity of absolute value of an. And that, if we take the given part, that's equal to negative 0, is just 0. So that's the limit of this part. That limit is equal to 0. What about the highest value, the right part? Absolute value of an, what is the limit? So limit absolute value of an as n goes to infinity, that part it's given, that's always a 0. So basically what I'm showing here is that the limit of this lowest value sequence, this sequence, the limit is always 0. it's always approaching 0. This limit, it's also approaching 0. If this the lower sequence has a limit approach of 0, then the higher sequence also has a limit approach of 0. Then the sequence in the middle, which is this part, this sequence will have a limit that's approaching 0. Because it's caught between two sequences. So that's approved. Okay. Any questions on this? There's a lot left, but that's okay. Any questions before I, so those are the three theorems, and also a lot of properties and the definition. It could be really confusing to you, like I said, but definitely try to understand the language here, because in the long run, it's going to benefit a lot from it. So here's the example. I'm not hearing any questions, so let's start looking at this example. We want to find the following limit. So find the limit n goes to infinity of n squared plus 100n divided by n squared plus 1. What is the limit of this? This is like a an, right? That formula gives you elements in the sequence. So if you expand it, you take 1 put in there, you got 1 squared plus 100 times 1 divided by 1 squared plus 1. That's the first element. Then you take 2 in there, that gives you a second element in the sequence. You put 3 in there, you get another element in the sequence. So what is those value approaching to? Right, that's a question. So there's a shortcut to this. I don't know if you would call it a shortcut, but there's a couple ways to go from here. The one way is to use the first theorem, that we can try to take the limit of the sequence. We can try to write it in terms of limit of function f of x, try to find the limit there. So let me try that. So I'm going to rewrite this as, instead of using n, I'm going to use x. So I'm going to write as a limit x going to infinity, x squared plus 100x divided by x squared plus 1. This I know is a function of x, right? So this becomes a limit x goes to infinity of f of x. The previous one I have, that's like a limit of a sequence an. So can I figure out the limit for this function? If you remember, we have done this before, right? If we want to take the limit of this, we can divide by the highest x term. So that will the highest degree of x. So that becomes limit x going to infinity of, I'm going to divide by x squared. And the simplified bit, that becomes limit x going to infinity of 1 plus 100 over x divided by 1 plus 1 over x squared. Keep in mind that x goes to infinity. If x goes to infinity, the 100 over x term will go to 0. The 1 over x squared term also goes to 0. And then we end up just taking the limit of 1 over 1 and just 1. So that's the limit of the function. And so limit, since limit x going to infinity, f of x equals L equals 1, so the limit exists. And f of x, if we replace x with n, so f of n will equal to n squared plus 100n divided by n squared plus 1, that's equal to an. Because of those two, therefore, we can just say the limit n goes to infinity of an, where an is n squared plus 100n divided by n squared plus 1, that's just equal to 1. So that's using theorem 1. Any questions on this? So the first thing, what I did is I take the an formula and the limit with n, and I rewrite it in terms of x and a function of f of x. Basically, I'm taking a discrete function, right? Sort of discrete function, and I'm writing it as a continuous function, and then use the continuous function to find the limit. I want to point out that this type of question in the future, you can do it directly. Just like we did divide by x squared, directly you just divide by n squared. So you can write as limit n goes to infinity, n squared divided by n squared plus 100n divided by n squared divided by n squared over n squared plus 1 over n squared. And simplify from there, so you get limit n goes to infinity of 1 plus 1 over 100 over n, and then 1 plus 1 over n squared, and then you take the limit at there, you get 1. It's the same part as the part that we divide by x squared, but I just want to show you that two different approaches. We can do this, it's because we can do it with a continuous function. So that's the limit of a sequence.
What is the difference? Like, what are the differences between those two? Because the only thing I really see is the variable.
It is a variable, but it's different. So, like I said earlier, in this notation, this formula, it gives you the value of elements in a sequence. A sequence, just individual elements, right, in a list. So that's what that formula gives you. So we're taking the limit of a sequence, that's the given part. Right? So what I did by turning it into, in terms of x, in terms of, x squared plus 100x over x squared plus 1. So what I end up with, this is not a sequence. This is a continuous function that depends on x. And I am taking the limit of a function. So that's the difference. So this is sort of going back to this diagram I draw. So one of them is taking the limit of those individual points, like the black points, the black dots I have. One of them is taking the limit of those individual points. The other one is taking the limit of that continuous function that I draw in the line there. So obviously they're going to give you the same limit, right? Because they overlap, but they're not the same. One is a sequence that you're working on. The other one is the function that you're working on. So that's the difference. But you can, like I said, because of this theorem, you can always use a function, f of x, to find the limit for the sequence. You basically take find the limit of the continuous curve, use that limit for the limit of that sequence. That sort of answer your question, Sam?
Yeah.
Okay. So yeah, just keep those in mind. So whenever you work with like a limit n goes to infinity of some expression in there. So here we talk about sequence. We're not talking about function that depend on n. We talk about sequence. Okay. Now, before I move on, I had to write down two definitions. Oh, not two, really, it's just brief one. So if limit n goes to infinity an equals L, which is a finite value. So if the limit of the sequence exists, then we say the sequence an converges. So the sequence will converge if the limit exists. And if the limit is not equal to a finite value, or we cannot find the limit, if limit doesn't exist, limit of limit an as n goes to infinity does not exist as a finite value. Doesn't exist or is infinity. We say then the sequence an diverges. So here's like a new term that's different from the integral. Remember last section we had an integral that's convergent if we can find the limit. If we can find the integral through the limit definition, right? So here we talk about sequence converges. That's a lot of terms here. So in the example I given above, this example, that sequence, so this, because we were able to find the limit as a 1, so this sequence, let me use a different color before we get confusing. So this sequence n squared plus 100n divided by n squared plus 1. This sequence for n goes from 1 to infinity, this sequence converges because we were able to find the limit as a 1. So just a notation on the side. All right, let me give you another example. This one is a little bit more challenging. We want to find the limit as n goes to infinity of this sequence e to the 2n over n . So here it's more complicated, right? We can't do the same way we did earlier by dividing by n or something like that. It doesn't work that way. But what I can do is again, I'm going to turn it into, so the sequence is e, if I plug in 1, 2, 3, 4 separately, so I get e squared over 1, that's just e squared. And then plug in 2 to get e to the 4th over 2, and then e to the, plug in 3, that's e to the 6th power over 3, and so on, right? So that's a sequence. I want to know, as n goes to infinity, is it going to approach to a certain number? So what I'm going to do is I'm going to turn it into the continuous function, limit x goes to infinity. I'm going to erase this sequence because we don't need it. I can't find it. So limit x goes to infinity of e to the 2x over x. Because it's a continuous function, we're not working with 0, so don't have to worry about denominator being 0, right? If you look at it, if we put infinity for x, we get infinity in the denominator. Numerator, we also get infinity. So this is like the form that we cannot determine from calculus 1. But we can try to use L'Hopital's rule. which means we're going to take the derivative of the numerator, take the derivative of the denominator, and then try to take the limit. So derivative of e to the 2x, that's a 2e to the 2x. Derivative of x is 1. So now we get rid of the denominator going to infinity. So now it's okay to take the limit as x goes to infinity. That's just going to approach 2e to the 2 times infinity. That's e to the infinity. That's approaching infinity. And this is not a finite number. In this example, we see the sequence that we're looking for. So the limit of the sequence e to the 2n over n, as n going from 1 to infinity, does not exist, because the limit of the continuous function that corresponding with this sequence doesn't exist. So that's one way to see it. Another way to say is we can see that the sequence e to the 2n over n diverges. Because of the limit doesn't exist, does not converge. Does not converge. So it diverges. I have two more examples. Let me finish, then I'm going to be, if you have questions, again, interrupt me, but I'm going to finish two more examples, then I'm going to stop, okay? I know you're probably bored already. So the next example is, I want to know the limit, or I want to know if this sequence, -1 to the n over n, as n going from 1 to infinity, I want to know if this sequence converges or diverges. Can we find the limit, basically? And what is the limit? Well, this one, if you remember from the early example, if we expand it, we will have the sequence is n equals 1, so that's a -1 over 1. N equals 2, -1 squared is positive, so we get positive 1 over 2. And n equals 3, I get -1 again, so -1 over 3, and the positive 1/4, and so on. Does this converge, or does it, if we take the limit, is the limit going to be a finite number? Okay. So the trick for this one is that, note, this is going to use the third theorem we had. Note, if we take the limit as n goes to, we want to know the limit. So let me write, we want limit of -1 to n of n. That's what we want. But note, the limit as n goes to infinity of absolute value -1 to the n over n, that is equal to, with the absolute value sign on that function, that is equal to limit n goes to infinity. We can just take the absolute value of -1 to the n, divide by absolute value of n, and n is going from 1 to infinity, so n is positive anyway. So that's equal to limit n goes to infinity of n in the denominator. The numerator becomes what? Becomes just 1, right? Whether it's +1 or -1, if you take the absolute value sign, it's just 1. What is limit as n goes to infinity of 1 over n? That is just going to be 1 over infinity. That's equal to 0, right? So the limit of the absolute value of this function goes to 0. So let me write down. So limit n goes to infinity, absolute value, -1 n over n, that goes to 0. Therefore, if we drop the absolute value sign, n goes to infinity of -1 to the n over n, that's going to be 0, using Theorem 3. which sets the limit of absolute value an as n goes to infinity. If that's 0, then limit n goes to infinity, drop the absolute value sign. That's also going to be 0. So that's the theorem we use. And then the last example, any questions on this? We got 4 minutes. It's plenty of time for me to go through the last example. Do we have to write when we use this? No, good question. No, I just want to point it out. You don't have to write. You can just, for you, let's say you are working on this example, right? You can just say, you can just keep this part and then directly conclude that this is equal to 0. You don't have to write down the rest. But I just want to show you, how we get to that point. So that's this one. The next one is we have a sequence -1 to the power of n, just that, as n goes from 1 to infinity. Oh, I didn't conclude, sorry. So because we found in the previous problem, because we found that the limit is equal to 0, that's a finite number, right? So the limit is finite value, the limit exists, therefore the sequence converges. So limit exists. So the sequence -1 to the n over n converges. I did not answer that part. Now this last one I gave you, it's just -1 to the n, for n going from 1 to infinity. Do you think this one converges or not? Any guess? Yeah? No? More yes than no. It's a no. I will show you why. So you probably think, can we just do the absolute value thing, right? Well, let's see what goes wrong if we try to use theorem 3. So theorem 3, so we can try to find the limit n goes to infinity of absolute value -1 to the n. That will just going to be just 1, right? Doesn't matter +1 or -1. When you take absolute value, you just get 1. You're probably saying, oh, that's just 1. Therefore, the limit n goes to infinity of -1 to the n is just 1. You probably think in that way, if you say yes. No, because this is the way it went wrong. So because the limit of the absolute value is equal to 1, so we cannot apply the theorem 3, because the theorem 3 says if the limit of absolute value an equals 0, so 0 is a key there, then we can draw the conclusion. But here, the limit of absolute value, of that an, -1 to the n, that's not even going to be 1. So cannot apply theorem 3 because limit absolute value an is not equal to 0. So we cannot apply that theorem here. It has to be 0 in order to draw the conclusion. So no, cannot use it to make the conclusion. Well, how do we find it? Well, let's just look at the Sam, that's a good question. I cannot tell you when to use which. You kind of just have to I would say practice. Yes, Aiden, good. I was just going to say practice. Yes, trust me, the more you practice it, the better. Try it, right? If you try to turn it into function f of x, So if it helps, that usually helps. If that doesn't help, try it with the other theorems. All right, so how do we, let me finish this and I'm gonna let you go. Sorry, running over a bit late and running over the time. So I'm just gonna expand the sequence. So I get -1, +1, -1, +1, and so on, right? And if we were just plotting them, +1, -1, and to see what the sequence, where the sequence goes. So we begin with a -1, and then we jump to +1, and then jump to -1, jump to +1, and then -1, and so on. So that continues. So the value here, by just looking at it by inspection, it's not the 1 and the -1, they're always going to stay separately, right? They stay parallel to each other. They're not going to converge. They're not going to try to meet in the middle, right? So those two values are always going to be separate. Therefore, it never converges. It doesn't have a limit as n goes to infinity. So for n equals infinity, how do you know it's going to be here or here? We don't know, right? It could be, it's just always oscillating up and down, up and down. So the sequence does not converge. The sequence diverges. So there's no limit that's approached that the sequence is approaching. So limit of sequence doesn't exist. The equivalent statement. So you can either see it diverges or the limit of the sequence doesn't exist. Right. I just want to use that example to show you that you have to be careful when you try to use the theorem 3. All right, sorry for being late. I'm going to let you go. I'll see you tomorrow. Definitely review what I did today and what we talked about before today. So this stuff about limits, that will be on the quiz. So we'll be on the quiz. So obviously, it's not going to be a too difficult example if we put on the quiz, right? But you need to make sure you're comfortable with finding the limits of a sequence. All right, take care. I'll see you tomorrow.